think of temperature as something to do with the jiggliness of the constituent particles within something. I will say that temperature and how we define it depends whether we're talking about macroscopic things. Now, a pea is macroscopic, it doesn't have to be huge, but something that contains many, many particles that aren't cohering together. In that situation, temperature is slightly different. It's the same, actually, but the things that matter are slightly different. So when we get down to the quantum level and we start talking about defined energy states, systems that only can take one of two or three energy states, temperature becomes more, and heat become more of a slippery concept, particularly temperature, down at those levels. I'm going to talk about everyday heat today, so we're not going to talk about lasing mediums and the stuff that, Shamash, that you got excited about, the negative temperature stuff. But I might redo that one that John did sometime and get into negative temperature my way. It's basically the same treatment that John gave, but I've got a kind of simplified way of going through it so that we don't lose the wood for the trees. You may have heard of absolute zero. People hear that that is the lowest temperature you can have. It's about minus 273 and a bit centigrade. It is the lowest temperature you can have. It is the lowest energy state of a system you can have. But actually, numerically, it's not the lowest temperature. And you will have seen in John's more recent biophysics on thermodynamics that you can actually have negative Kelvin, negative absolute temperature, which was mind-boggling when I first heard about it. And Shamash, is your mind still boggled about the idea of negative Kelvin, or has it stopped?
No, I'm completely and deeply. I completely and deeply understood it, but it's still mind-boggling because the way we learn about temperature is that it's this absolute scale to measure heat, and it's not the other definition with the derivative, etc. Like that's just another quantity, and this is not heat. This is temperature, and temperature could be negative when the derivative is it's sloping. When the tangent slopes down, it could be negative. So yeah, that's just amazing.
Awesome. Well, I was pretty mind-boggled by it. But today we'll keep it into the everyday intuition. But our intuition, even without getting into things like negative temperature, can get defeated. One way is by considering situations in which you're below absolute zero, which I won't go into the details of today. But another one is, it struck me when I was at the Institute of Astronomy nearby in Cambridge here. And they were talking about the temperature of certain interstellar gases being tens of thousands of degrees. At tens of thousands, it doesn't really matter whether we're talking about Kelvin, Fahrenheit, or centigrade, really. They're all tens of thousands. There's always tens of thousands in all of those, if you're being that vague. So hot, but yet incredibly cold. So very high temperature scale measurement. But if you were out there, you would lose heat to that environment very rapidly. And the reason is because we're used to, if we're talking about the temperature of a gas, we're used to talking about gases at reasonable pressures and reasonable densities. Whereas out in interstellar space, you can have situations in which you only have one gas molecule every cubic meter or something like that, in which case the temperature of that gas can be extremely high, yet the energy contained with it, the thermal energy in there, is incredibly low. So actually you would lose your heat as a dense human full of molecules packed in very, very tightly. You would lose heat to that environment really quickly. So things can read as hot, theoretically be very hot, and yet feel very cold. And there are other places where our intuition fails. There's like cold stone floors, that we stand on a stone floor and we swear blind that that is colder than a carpet or a wooden floor, whereas actually if you leave, if you have a room that has both a carpet and a stone floor in it, then if they've been sat there for a long time, they must be at the same temperature. You can prove they are by just measuring it with a thermometer. But yet they feel incredibly different in temperature, and that's because the stone floor takes the heat away from your foot rapidly, whereas the carpet doesn't, tends to reflect the heat that's in your foot back. So our intuition around temperature can fail us quite a lot, and we'll try and shore that up a little bit today as we go through. So slides are at the top of the room. Welcome to new people who have come. You're very welcome. We'll go for about an hour and a half here today in total, and we're going to cover heat first, and if there's time for another topic, we'll move straight on to another one. Any questions or feedback or anything? By the way, do ping your friends in while I cough. Excuse me, while I stop for a sec to cough. Okay, there you go. Hopefully I muted that properly. So I'm not going to bore you about the temperature scales. We've already alluded to them. It might just be worth mentioning why they're what they are. Fahrenheit's basically built around humans. 0 is around about the freezing point of your blood. And 100 is around about as hot, Fahrenheit is around as hot as you want to get before you've got a fever. So you can think 0 to 100 in Fahrenheit is quite a nice temperature scale in that it's very human. 0 is too bloody cold for us. and Fahrenheit, that is, and 100 is getting too hot, far too hot for us because it's at the extremes of what our body likes to operate at. Fahrenheit's is these temperature units are they're bigger than they're smaller is the better way of saying it, than the centigrade. There's 9/5. That's the ratio. So for every 9/5 of a which is about 2. Every 9/5 of a Fahrenheit you go up, you've gone up 1 degree C. I think we know what degree C is. 0 is boiling point. 0 is the freezing point of pure water. 100 degrees is the boiling point of pure water at sea level. Anybody know what the boiling point of water is up Mount Everest? If you try and make a cup of tea up Mount Everest, roughly, without Googling it.
What is it, 60 something?
Yeah, I don't know exactly, and it's going to depend on a few things. But yeah, high 60s, low something like that, low 70s Celsius.
They say it's impossible to boil potatoes up there.
Probably is, yeah. You're going to get a very boring, mediocre cup of tea up there, and yeah. And that's simply because the pressure is too low. There's not enough atmospheric pressure to hold the molecules down as you heat them up. So the point at which you get to molecules escaping the surface of the liquid due to vapor pressure is much sooner when you're that high up a mountain, because there's not enough atmosphere above pushing down and keeping it in liquid state. And then Kelvin is the real temperature scale that scientists use. It's the same unit size as centigrade. So centigrades are 5/9 of the size of a Fahrenheit and vice versa. But Kelvins are the same size. So 1 Kelvin is 1 centigrade, but it just starts at just over -273 Celsius, which is about -460 Fahrenheit. And in very simple terms, all the jiggling stops down there. In more complicated terms, there's better definitions of 0 Kelvin.
Ben, we have a question in chat. Ayo Wizzy is asking, so Fahrenheit is lower to degree. He thought it was used based on different countries.
Yeah, I think it's pretty international. I think it's pretty standardized. That 0 degrees Celsius, I think it's -32 Fahrenheit. Is that right? Have I got that around the right way? I'll tell you how to convert between them in a second. So no, it's standard. It is standardized. 0 Celsius is 32 Fahrenheit, not -32. And I can tell you a quick and a slow way to convert between them. And this is actually more useful, more interesting, because in general, the fact that there are multiple ways of doing this kind of talks to, in physics, there's often multiple, in life there's often multiple ways of doing things. The quick and dirty way that's good enough, and then the correct way that's slower to use, and yet more precise. And it's really good to have the wisdom to know which one to use, right? So for everyday temperatures, what we're talking about to get from centigrade to Fahrenheit is doubling it and adding 30. That's the rough and ready way. That's basically never correct. That's only correct at 1 temperature. Bonus in the chat for anybody who can tell me what temperature that is right at, by the way. When is doubling it and adding 30 correct? At which temperature is that correct? If you want to guess in the chat, let me know. So that's the quick and dirty. So we have 20 centigrade, we double it 40, we add 30, 50, 60, 70, we get 70 Fahrenheit. Now, the good thing about that, as I say, it's fast. We can do it in our head. Double it, add 30, easy. Now, the correct way, we already said that a Fahrenheit is 9/5 of a centigrade, right? So a better way to do it is to double it, which gives you 10/5. Take off 10%, which takes you down to your 9/5. So you're 20 degrees C, but you double it, gets 40. Take off 10%, well, 10% of 40 is 4. So 40 minus 4 is 36. So now you're down to 36. So your 20 becomes 36, and then you add 32, which gives you 68, which is very near the 70 of our estimate, but it's not exactly the same. So doubling it, taking off 10%, which is the effect of multiplying by 9/5, and adding 32 is precise, because 32 is the offset. 32 Fahrenheit is 0 Celsius. But that's a lot more cumbersome and slow. And the bottom line is that for everyday kind of weather type temperatures, doubling it and adding 30, and by the way, you can reverse these by doing things in the other order. If you have 80 Fahrenheit, you take 30 off, 70, 60, 50, and then halve it, 25 centigrade. So you take off 30 and halve it if you want to go the other way. This method is good enough for everyday like weather type temperatures, and then becomes very inaccurate as the temperatures get very high or low, in which case you need to double it, take off 10% and add 32, or multiply by 9/5 and add 32. So that's that anyway in terms of conversion. Hopefully that answers the question. And thanks, Shamash, for telling me there was a question. I need to pause to cough. Ah, lovely.
Is it negative 16.6 degrees?
don't know. We're going to have to let other people have a guess. Is that what you've calculated?
I haven't calculated this before, but yes, that's what I roughly did. Yeah.
Okay, sounds about right. I don't actually know the answer. I'd have to do the very simple simultaneous equation that it is to work it out. What's that in Fahrenheit?
What's that in Fahrenheit? Depending on your quick trick or on the actual definition.
Well, either.
So I'll tell you what I did. I solved the equation 2x plus 30 equals 9/5x. So doubling and adding 30, when is it the same as 9/5?
Yep.
Yeah, it gives negative 16.6 degrees.
In centigrade?
Yes, hopefully.
And what's that in Fahrenheit? Yeah, I think it isn't right, by the way. I think it's 10 degrees.
Minus 29.88 Fahrenheit.
I think it's 10 Celsius. If you take 10 and you double it and add 30, you get 20, and you get to 50. If you take 10, you double it, you take off 10%. So that gives you 20 goes to 18 and add 32, then you also get 50. So it's 10 degrees Celsius, which is 50 Fahrenheit. That's the one temperature at which the approximation is correct. So close, but no cigar.
Very far away, actually.
A bit disappointed for the mathematician, but it's okay. It's 10 degrees. So different ways to measure temperature we might see every day. Dry bulb, wet bulb, and infrared. They're all different, and there's other ways, but these are three common ways. So firstly, let's talk about dry bulb. When you see the weather on the news, etc., they'll give you what's called the dry bulb temperature. So bulb literally means the bulb of a thermometer, you know, the bulbous bit at the bottom. Dry means that it's dry. It means that it's not wet. And it's also in the shade. You have to take, for purposes of measuring air temperature, you must take the temperature in the shade, because how hot something is in the sun just depends on well, we'll talk about that when we get to infrared, but it can really, really vary, as you know, from touching like a hot, like car bonnet or something on a really hot day. It can be much hotter than the air temperature. We'll talk about why in a minute. But dry bulb is one. So you put a thermometer in the shade, it's dry, and that's the dry air temperature or dry bulb air temperature. It's fine, it's good, it tells you what the dry temperature is. It doesn't really tell you how hot it feels. We can tolerate very high dry bulb temperatures, like 100 centigrade in a sauna. A sauna can be 100 degrees centigrade. It's unbelievable to actually realize that it's actually boiling in there. Literally 100 centigrade. And we're fine, as long as some idiot doesn't go and pour too much water on it. And then the humidity starts going up, which is where we go to the second form of temperature, which is wet bulb. That's where they still have a thermometer in the shade, but you wrap the thermometer with a wet rag, or a rag you kind of keep wet. It's a bit more technical than that, but that's the basic point. And this simulates the ability to lose heat through sweating. And it measures what change in temperature you get due to evaporation. And if the air was completely dry, then the dry bulb and the wet bulb temperature would be the same. But as the temperature goes up, then what happens is you get more and more, as the humidity goes up, you get less and less ability to evaporate. And you start to see a discrepancy between the dry bulb and the wet bulb. And it's actually high wet bulb temperatures that we are unable to tolerate. They get really uncomfortable. So they don't give that in the weather. You can calculate the wet bulb from the humidity, the relative humidity, and the dry bulb. But watch out for that. If you go searching for it, you could probably Google right now and just say wet bulb temperature, I don't know, let's just say in San Francisco. Let's see what we get. And it doesn't come up immediately like as quickly as I'd like it to, but if you click into a website, you will find it, and you'll be able to see the difference between wet bulb and dry bulb. And if you find yourself a nice source of wet bulb temperatures, you might find they're much more useful in terms of how hot you feel, because they take into account how much air temperature can be lost by the thermometer in the shade due to evaporation. And that depends how wet the air already is. If the air is really dry, then it can lose a lot of heat to evaporation. And if the temperature is really wet at the extreme, it can't lose any because the air is already saturated with water. So I hope I said it around the right way in the beginning. I might have said it backwards, but you get the idea. And then the final one is infrared. You can point one of these infrared thermometers that were all the rage during COVID. People would zap your forehead with this little infrared thermometer. And that's looking at, it's not actually measuring temperature directly, it's looking at the amount of infrared that's being emitted from your skin and making some assumptions about how your skin radiates, something called the emissivity of your skin. These little infrared thermometers you can buy typically assume 0.95 emissivity, which means basically that it transmits heat 95% like a pure black body. Things that are purely black emit heat in a very characteristic way, emit infrared in a very characteristic way, and then as they become more shiny or more white, then the way that they transmit infrared becomes modified. So let's go back to that car bonnet for a minute. That something sat out in the sunshine and it gets really hot. How can it be hotter than the air temperature? Question to the audience. How come you can pretty much burn your hand on a car bonnet or on your dashboard or on the sidewalk sometimes? What's going on there? Anybody want to explain it from a and hint, use infrared in your answer. Let's see if anyone wants to explain. Shamash or anybody else?
I can try. I don't even think I know the answer, but because it's been on the sun, under the sun too much, it has stored so much of that heat, and so to use infrared in the answer, it's giving off infrared radiation when you touch the bonnet, and so you could burn yourself. There you go.
Great, just strap infrared onto the end and everything.
Well, you said that I'm following directions here. You have to get the full points, right? There's an extra point for using infrared in the answer.
You did well.
Can I get a bonus point for using entailment in the answer?
No, definitely not. No, I'm not as enamored with that word, although it is still nice. So yeah, cool. The question then, if it's because it's been sat there a long time, as you say, absorbing heat, why doesn't the same thing happen just with the heat from the air? So something's been sat on in hot, why doesn't the thing in the air in the shade ever get hotter than the air temperature, yet the thing in the sun can? You ever thought through that? Because the thing in the shade, by your idea, could in principle sit and, quote, absorb or whatever, soak up the heat for a long period of time, but it never becomes hotter than the surroundings in the shade. But in the sun, all bets are off. I can tell you what it won't get hotter than in the sun. Nothing sitting in the sun will get hotter than 5,700 degrees Kelvin.
That's the temperature of the sun, yeah.
That's the temperature of the surface of the sun, yeah. But beyond that, I can't really tell you how hot something's going to get in the sun without knowing a reasonable amount about its material properties, the atmosphere, the sunlight, etc. Hey, John, welcome, by the way. So that still remains the question. Why does something sitting in the shade typically get no warmer, like a dry bulb thermometer, which is the very way of measuring dry temperature, doesn't get warmer than the air temperature? But something sitting out in the sunlight does and can.
But because it's interacting with the air, so it's getting the thing sitting in the shade is getting the temperature from the air, and it's also losing temperature to the air at the same rates. Whereas something sitting in the sun is interacting with the air in that manner, but is getting the extra energy directly from the sun.
Okay, I quite like that. That's getting much closer. Well done. Yeah, I think that sounds a lot closer. So we're talking about something called thermal equilibrium, right? You put a cold thing in the shade, and what's going to happen, in stable air temperature, is that you're going to have literal molecular interactions at the surface of the cold thing with the air, and over time, heat is going to flow from the air into the cold thing until the cold thing is at the same temperature. It'll flow in slower and slower, by the way. So initially fast, as you know, things that are big temperature differences lead to high heat flow rates, right? So you bring this cold thing into warm air outside, for example, it'll warm up and warm up and warm up at a decreasing rate, but eventually will end up the same temperature as the air, as long as the air is stable. Real air changes temperature constantly, so the thing might be following the real air temperature constantly. But imagine the air temperature is constant; it'll get there eventually, as you said. And then it's in thermal equilibrium. The only way it can lose its heat to that air is conducting heat, radiating heat, or convecting. Now, convecting is kind of like conducting. Convecting just means that you conduct into the air, and because the air is fluid-like, it moves up and away. Fresh air can come in from below. That's how a radiator works. They call it a radiator in a house, but they really mainly work by convection. And it means that you're setting up an airflow. They're the mechanisms at play. But if the thing is in the shade, then it's typically going to, any energy it loses by radiation is typically going to be similar to the amount of energy it's gaining by radiation from around the outside. Very different when you're in the sun. When you're in the sun, it's doing all the same stuff with the air that we talked about, But the overwhelming effect, especially if the thing is black literally looks black, certainly if it looks black in infrared, is it's going to be receiving energy from the sun at about 1,000 watts per square meter, something like that, to give you an idea. That's about like sunlight intensity at the surface of the Earth, about 1,000 watts for every square meter. So a big TV, normal sized TV is 1,000 watts of heat. That's a lot. It's why you should leave in a cold climate. It's why you should let the sun stream in your south-facing windows if you want some free heat. It's actually, a 2, 3, 4 square meter window gives you 2, 3, 4,000 watts of heat energy in the summer. It's pretty cool. Well, it's pretty hot actually. So this thing's gaining heat from the sun, and its temperature will continue to increase towards the surface temperature of the sun. But as you said, Shamash, as it gets hotter, it's also going to be radiating more and more by infrared, and it'll end up in an equilibrium where the amount of heat, the rate at which it's losing heat, is the same at the rate, because it's hotter than it was. It's the same at the rate as the rate at which it's gaining heat, and it'll come into equilibrium. But it's not just about the radiation. As the surface of the thing gets hotter, it will also conduct heat faster into the air and convect faster, which just means that the conduction leads to airflow. So yeah, it's not. That's why I said I can't just tell you straight away how hot something will get. It depends on when that becomes imbalanced. The radiation coming in, and then how's that heat being lost by radiation of the thing and convection and conduction. And you get some temperature. Now it could be, I don't know, it could be 200 Celsius if it's the right thing in the right circumstances with limited of convective cooling ability. It might only be a bit higher than the air temperature. It could even be more. I don't know how hot the hottest thing got in sunlight. If anyone wants to Google for it, you're welcome to. The hottest theoretically it could ever get is the same as this temperature, surface temperature of the sun. John, you're here. You're not supposed to be here. You're spying on us. How are you?
Yeah, so I am here, but I'm on my way to Vegas.
Oh, wow. There you go. That's pretty cool. On your way to Vegas. There you go. There you go, Shamash. You know what he's doing? He's going to party. In his mature years, he's still...
Shame.
I'm going to see eagles at the Sphere, and hopefully see
cool.
Rohan, but I don't know. We'll see.
Oh, that'd be cool to meet up with Rohan. He lives there, doesn't he?
He does.
Yeah, that's pretty cool. All right. So let's get finished off on this presentation bit, and then do entirely Q&A. So what else to tell you about heat? I'll just to mention a few other things. The units, you'll hear lots of different units. Energy ultimately is the unit. So joules would be the standard, the SI, the System International Standard. But we can also hear it quoted in kilowatt hours, which is a bloody awkward unit, but it's what we seem to use for electricity. We take something like kilowatts, which tells you how much energy per unit time, and then we multiply it back by unit time to get energy. The kilowatt hours confuse the hell out of everybody. But anyway, that's what we use, and it means you are exerting a kilowatt of heating effort for 1 hour. That gives you a kilowatt hour. A kilowatt is 3,600 joules per second, by the way. So joules is 3,600 joules per second times 1,000 to make it a kilowatt, times it tells you how many joules there are in kilowatt hours. And anyway, I don't know why we did that. Calories would be another one. Calorie isn't as useless a unit as you think. 1 calorie is the amount of energy required to heat up 1 gram of water by 1 degree C, by the way. But when we say calorie, we nearly always mean kilocalorie. When we're talking about food, we don't need 1,000 calories a day. We need 1,000, a million calories a day, 1,000 kilocalories. But it just often gets dropped. But definitely when you're talking about like food, for example, it's kilocalories. And the way you can tell, one way to tell whether you're dealing with calories or kilocalories is just to remember what a calorie is again. A kilocalorie is 1,000 calories. That's enough to heat a litre of water by 1 degree C. Whereas a calorie is 1,000th of that. It's enough to heat a gram of water, like 1/5 of a teaspoon of water, 1 degree C. So you can probably work out, because they're 3 orders of magnitude difference, you can probably work out whether people really mean calories or kilocalories based on the definition of a calorie. Another quick thing to say about heat is, whereas the units of heat is energy, it's not all equivalent. If you have a unit of electrical energy, typically, unless it's at really low voltage, then it can become a bit useless. But if you have electrical energy, it's typically as good whether it's, well, just, I don't care where you get it from, right? I don't care whether it's in a battery or whether it's in the grid or where it is, you can convert it pretty efficiently from one form to another, unless it's really, really low voltage. And you can use it for heating, you can use it for mechanical work, you can use it for computers, you can use it for lots of things. It's a very pristine form of energy. Whereas heat, the colder it is, the more that all you can use it for is just heating something else to that sort of temperature. So if you have something like water at 100 degrees C, it's great for, well, showering if you mix it with some cold water, or for heating up spaces like radiators and stuff like that. But you can't like turn it into electricity with any efficiency whatsoever because it's too cold. So if you have X number of kilowatt hours of heat at low temperature, even though you may have the same number of kilowatts hours of heat at a much higher temperature, you may have sound like you have the same amount of energy, your options as to what you can do with it at high temperature are much higher. If I have heat at 10,000 degrees C, I can turn that into superheated steam and make that very efficiently into electricity, with which I can then do whatever I like, as I said. So just bear in mind that not all heat is created equal, even though it's the same amount of energy. We want high temperature heat, really, but it has its own problems. It wastes way more quickly, it's harder to deal with, it's more expensive to move around, etc. So that's that. I don't really know how much more we want to do. Yeah, I will just tell you about the two different main ways heat moves, radiation and convection conduction. And then I think I've got a bunch of questions. So they'll be quite fun. That'll be quite stimulating for the discussion. So the questions are on the last slide, slide 8. So click the link at the top of the room, go to slide 8, and we can start thinking about. Might be good to look at the questions now. And then then I'll do the last bit. I'm going to read the questions out, actually, on slide 8. Then I'm going to tell you a few things about the way heat moves, and then I'm going to see how many of you can get the answers to these questions. So I'm going to rattle through the questions, and then we'll discuss them after this bit. How come we can walk on hot coals? That would be a good question. Why does a stone floor feel so cold compared to a carpet? I've kind of told you that. Why can you take tin foil, aluminium or aluminum, if you're afflicted with that disease you guys have called American? How come you can take aluminium foil out of the oven with your hands, regardless of how long it's been in there? Yeah, that's probably, I'll leave the other one. One more. Why would we use a ceiling fan if it heats the room up? So there's an implicit answer in that question, or there's a statement in that question. My statement's going to be that a ceiling fan heats the room up. So how come, and why do we use it? So they're the questions, and before we have everybody kind of try and answer them, and we'll try and get through all 5 of them, or 4 of them now, let's just talk briefly about one last thing, which will help you answer these, and then we can just chat from there. So heat moves, one way is radiation, depends on all sorts of things. It depends on the surfaces, something called the emissivity of the surface. If a spherical body like the sun, black body like the sun, which emits in a very characteristic spectrum, is emitting heat, the amount of heat at a given distance for it falls off according to the topic we didn't cover today, which is the inverse square law. That basically says if you double how far away you are from it, you get a quarter of the amount of heat. If you triple the amount, 3 times 3, which is 9, you get a ninth, and so forth. So the heat falls off pretty rapidly, which shows you just how darn hot the sun is, right? That we're all this distance out, 100 million miles away, and it's still as hot as it is, despite the inverse square law. How much heat you end up, how hot you get because of radiation depends on you as well. It depends on, that's why we wear hats on a hot day and we put ourselves in the shade. It depends on your characteristics, your color, your reflectivity, your emissivity, and your temperature, crucially. Radiation doesn't need a medium to transfer. I don't mean a medium as in people who claim to talk to the dead. I just mean it doesn't need anything to go through. A vacuum will do fine, which is pretty cool. And the main way that heat is transmitted is through the infrared part of the spectrum, but actually the whole electromagnetic spectrum emits heat and transmits heat. We just talk about the infrared because hot things that we're used to, like fires, tend to emit most of their energy in the infrared part of the spectrum. Not so for the sunlight, actually. I think most of sunlight's energy is in the visual part of the spectrum, although if John's unable to unmute, he can probably confirm that. But I think that's the case. But we're just used to talking in infrared because that's where most of the heat comes from hot things. So then the other mode is convection or conduction, and that's just literally surfaces being in touch with each other. And if there's a liquid or a gas present, then that makes the liquid or gas bubble up and move, and that becomes something called convection. So that's it. We'll get on to the questions. So let's do it. So question 1, I'll paste them in the chat. How can we walk on hot coals? Let's see. Let's get some people on the stage answering, or come up from the audience, or just shout up in the chat if you prefer. Why can we walk on hot coals without getting burnt feet?
Is it because you have fasted for 3 days before the event and you prayed for the god Krishna?
No. It isn't, despite what people will tell you. That is what I would class as utter bollocks. So what do you want a more scientific reason why you can walk on hot coals? Come on, have a go, Shamash, or somebody else on the stage, or somebody in the chat. Why?
You have Sam 137. He is on stage now. He can answer.
Okay. Yeah, I'm gonna give it a shot. I think it has. Hello, Ben. I think it has something to do with the how smooth the surface of the coal is. So yeah, its radius 100 degrees, but because it's not entirely smooth like a mirror surface, it does not transmit the heat immediately to your body in a way that makes it burn your skin or feel the 100 degrees. I don't know if that's right.
Well, that's interesting. So my normal top level answer to this is as follows, and then we'll break it down into what elements of what you've just said. It's pretty interesting, actually. So my top level answer is this: that the coal is wood, and that wood doesn't have very much thermal heat capacity, especially when it's in coal form, because coal is light, right? So things that are light typically can't hold a lot of heat. We kind of know that intuitively. And things that are very heavy hold a lot of heat, right? We know that. A big boulder will hold a lot of heat. Now, obviously, the heat capacity of materials depends not only on just their mass, it depends on other things, but if you were to scatter chart loads of different materials, you'll find that they mount things of different weights and different materials. You'll find that really the predominant factor as to how much heat you can hold is the mass, your mass, how heavy you are. But obviously things vary. So coals, charcoal, they're very light, they're very low density. They can't actually hold that much heat energy. So that would be one thing. And then the other thing is they're not very good conductors of heat. Wood is quite a good insulator. It feels warm because it doesn't take the heat away from your foot. And if it is hot, therefore it can't give you its heat very fast. So it hasn't got you much heat to give. And when it does try and give it to you, it can't get it to you very fast. Now, your 2 points are interesting because they might go some way to explaining why the wood can't give your foot the heat very fast. Let's think about it. You said it's a bumpy surface. I mean, that's reasonable to a large extent. That's not about necessarily the fact that it's wood, but you're saying that if it's like a mountainous surface in contact with your foot rather than a smooth surface, there'll be less contact area for conduction. That's feasible and possible. It might be one of the reasons why wood is lower thermal conductivity. I don't know.
It's like when you have a book and a plate of aluminum, and they're equally have the same degree, but you can feel how cold the aluminum is, but you cannot feel you just made that example about the carpet and flats I don't know something else, and you said because it does not make any sense and to intuition in terms of of how intuition works, you could have two surfaces that have equal degrees of temperature, but some the other thing could have some sort of a not smooth surface, and this is why you cannot feel it's not very conducive to feeling the actual temperature of I don't know the surface or the surfaces we have in between hands to study such a thing. I don't know if I think that I just complicated it.
And Saran has just introduced another factor, which is the short contact time, and I think that's really important as well. So how hot your foot gets in contact with something is going to depend on a few things. Let's think about it. It's going to depend how fast the heat is transferred, so in watts, which is units of energy per unit time. Now, how hot your foot ends up getting is going to depend on how long you're in contact for, right? Which is, we know we can touch things that are extremely hot very briefly, for example, with our hand. And we're okay, because one of the reasons is there's not enough time for a lot of heat to transfer. It might transfer fast at a high rate, but there's not enough time for much of it to transfer. So I think that's a really important point as well. The basic point is the wood has less heat energy than you'd think, because it's wood and it's charcoal and it's pretty light. Even though it's hot, it doesn't actually have that much heat energy. So if your foot does take heat away from it, it actually it cools the charcoal down pretty quickly. You're not in contact with it very long, so it doesn't have time to heat your foot up. And the charcoal's not very good at getting the heat to you in the first place. So there you go. I think that's a good enough answer for why you can walk on hot coals. I don't, unless anyone wants to add anything, we'll move on to the
maybe some dead skin on the bottom of your foot would help. I also not isolate, but like you will feel less pain as you jump from one step to the next, and so as your foot is in the air between the two steps, kind of cools down, and then you have that cushion of dead skin on the bottom to help kind of during those couple of seconds of contact.
Yeah, that could affect how the point about it cooling down, I think, is an important one. The in between steps, the ratio of time you spend with foot in contact with the hot coals versus in the air cooling down, I think, is an important point. So anyway, yeah, cool. Lots of practical, sensible things. Thanks for that.
And praying to the god Krishna
definitely helps. Definitely helps.
I was going to say too. I thought the answer was interesting especially with the inclusion of the idea of smoothness, and I think the smoothness kind of had to do, in some sense, that's a word you use if you're talking about kind of a solid surface. And I think I may be wrong about this, but I think a lot of what goes on in the walking on hot coals is because it's not coal anymore. It really is mostly ash. And it has, far less heat capacity. To the extent that there is coal, you do want to make sure that there's a nice big layer of ash that has almost no heat, but is really hot and glowing.
Yeah, when I walked over them a couple of times, I don't know that there's that much ash on the top, but there may have been. But you can get surprising what you can.
Yeah,
get
I
away
don't.
with.
You probably know better than I do because I haven't done it and won't.
Yeah. It works. It's fine. But I didn't believe the praying bit to keep you, to protect you, and didn't need to. Still didn't get burned. All right. So let's move on to the next question. It's quite similar in a way. Why can you take? It is a fact that you can take aluminum if you must, foil out of an oven, even if it's been in there wrapped around your favorite Thanksgiving turkey for hours, at a very high temperature. So the oven itself, of course, will burn you immediately if you touch the sides of it. So will the baking tin. Why can you just stick your hands in, grab the aluminium foil and take it out and handle it as much as you like and you won't get burnt? What's going
I
on
have a
there?
first question before we go on to that. I want to know if in England that N in aluminum is sandwiched between two eyes or not.
I don't know if we spell it differently here. I don't even know how we spell it in the UK. Presumably the same as you.
So you just pronounce it wrong.
We call it.
It's aluminium and
No,
enough about this.
actually we do have a different spelling. So you guys
Is
guys
that
are
right?
yeah, you guys are so dumb that you couldn't handle aluminium because you'd have to actually like move your lips and pronounce more than one phoneme. So you simplified it to aluminum, which was preschool level pronunciation. But it is actually originally spelled aluminium, which I appreciate is a bit much for an American. So no offense to you Americans, I love you all. But yeah,
the whole point is to annoy British people, so it's working quite well.
It's working perfectly. Great.
It's recreational for us.
Yeah, it's all good fun. Okay, yeah, cool. So let's tinfoil. Why does that? How come that works? It does work, but how come? I've got some. Hey, you see, I sidestepped the whole issue there. I called it tinfoil. You see what I did there?
I did. I was going to call attention.
Wait. We have.
Hold on, Shamash. John's struggling with reception. Try again, John.
I was going to call attention to it myself, but I thought, no, only an asshole would call attention to the fact that you did that.
So that was me that did it then. Me that brought attention to it.
There you go.
So yes, why can we take this aluminium tin, whatever the fuck you want to call it, turkey
I,
foil?
can I just ask, can you really take the aluminum? Because I burned myself a couple of times doing this.
Well, if
So
it's
now
not,
now
yes,
I know to wait for a little bit and then touch it. Maybe that
well,
helps.
okay, let me be more clear on the parameters. If the foil is dry, not covered in turkey drippings, if the foil is loose, not scrunched up, right? So if it was scrunched up and you grabbed it and squeezed it into a ball and put it in your hand, yeah, that'd get pretty hot because you've got yourself a dense lump of metal in your hand. But if you just grab the open, loose foil and it's not got liquid on it, then you really shouldn't. I've never done this at ridiculously high temperatures, but you shouldn't get burnt. I've never got anywhere near getting burnt or even felt that it's hot. The question is why.
So is it because it doesn't return the heat? Retention of the heat?
Hey LT, nice to have you here again. Yeah, I mean basically this it's so low density, it's so light, the foil, that the bit of foil you're touching, if you think about how light that is, it only weighs a fraction of a gram, right? The little bit that's between your fingers that really matters. Maybe a few centimeters around your finger matter, but there's a limit to how fast the heat can conduct sideways through the foil and into your finger. So if you consider, I don't know, a few centimeter disc of foil, it's so light, it's a fraction of a gram. So it's the same thing again, it just doesn't have much heat energy in it. If your finger will take the heat from that foil, but then the foil cools down just immediately. And I think it's as simple as that.
But like, Ben, I have like another take on that question. Wouldn't you say because of like how fast like the aluminum loses the heat? Because I'm a smoker. I smoke, and it happens to me for like from time to time that I drop like a small piece of ash, like something extremely unmentionable, and it would like burn my hand and cause like leave something, and it's extremely light, extremely like as much as like the tin foil. Wouldn't you like in that case, because if like a small piece of ash could like burn my hand while smoking, attribute like that non-burning, not getting burned from the tinfoil to how fast it loses heat as soon as you open like your oven.
It will lose heat pretty fast as well because it's a metal and it's going to be just radiating that heat away. But I still think the predominant thing is it doesn't have a lot of heat energy to give you. With your ash, it's probably something more subtle happening. It's probably a globule of stuff that falls off the cigarette, inside of which there's something really warm, probably insulated as it falls by some ash around the outside. So firstly, it's probably much hotter, and secondly, there's probably a little tiny insulated element in there that when it hits your hand, the stuff on the outside falls away, and the hot core hits your hand and burns it, something like that. So yeah, that's another interesting case. But I think the main reason with the aluminium foil is just that it doesn't have much heat energy, because it gives it to you very fast. It's metal. It just doesn't have much to give you. And we could validate this, right? The way you'd validate it, you'd take the foil and you'd quickly transfer it into something like some water inside a polystyrene temperature cavity, basically, some water in something where you can measure the temperature rise of the water and determine how much energy there is, or you could calculate it. There's lots of ways you could work out what's really going on, but I'm confident you're going to find out it's because the foil is just light. And the other way is just make it into a compact, tight ball first, and then try taking that out and holding it in your hand, and then you'll find out how hot it actually is.
Or I was going to say, do the same thing with like I don't know, even a thin plate of metal, like a 16-inch. You would have a very different experience if you grabbed a 16th-inch thick piece of aluminum.
You certainly would.
Right.
Yeah, exactly.
Yeah.
It's the thickness of it. It's basically.
Yeah, it's totally the thickness, because it also, like, aluminum has a pretty high capacity heat and is also very conductive. So those are the two things you want to avoid if you don't want to burn yourself. But I think it's strictly because it's so thin, and there's just very little heat there to begin with.
Yep, exactly. Exactly. Thanks, Hira. All right, cool. So let's move on to another little brain teaser. I think I'm bored of heat transferring into our feet and hands. Let's make one last question as follows. Firstly, why do I say that a ceiling fan heats a room up? This is a two-part kind of challenge and question. Why do I say it heats the room up? There's three-part. Let's make it three-part. Okay, one, why do I say a ceiling fan heats a room up? Number two, how much, at what rate does a ceiling fan heat the room up at? How would you find out how fast it's heating the room up in terms of watts? How many watts of heat does a ceiling fan put into the room? And number three, why do we turn them on if it puts heat into the room? Why does it make us cool?
Let's make it fourfold. Why does the ceiling have fans?
Oh, shut up. Well, the 4 is 3 basically, because 3 is why do we feel cooler? So they have fans because they make us feel cooler, so we stick them on the ceiling. So let's start off with why do I say a ceiling fan makes the room hotter? I don't mean an air conditioner. I mean a ceiling fan, or just any fan.
Well, one way would be that the energy put into the fan is causing friction in the air and is heating the room up. That would be a vanishingly small amount. So I hope you don't mean that. But it also transfers air around.
There's the electric circuit as well.
Well, hang on. Let's explore that bit, Hiro.
Okay.
Let me make an even more bold statement. Even if the ceiling fan, you say it's vanishingly small. I don't necessarily agree. Let's answer the next. Let's answer the middle question next, then, and then we'll come back to the first one, then go to the last bit. The middle question is how many watts of heat does a fan put into your room? How would you find out? You can just look at the fan and find out.
It's written on it, no?
Well, the power that the electrical power that the fan consumes is written on it. How does the amount that the fan heats the room compare to that? If I have a 20-watt fan, how much heat energy is it putting into the room?
Michael Volt is on stage.
Okay, cool, Michael. So a 20-watt fan or a 100-watt fan, how much of that is
Hey,
turning
Ben, how's
into
it
heat
going?
in the room? Yeah, good, mate. Good to see you.
I'd like to chip in if you don't mind.
Yeah, chip in.
Well, it wouldn't be the rating of the motor. You would definitely need to know a couple things. That would be helpful. You would know what the motor efficiency is. Therefore, you could find out how much heat gets radiated from the motor. Because not all the energy, not all the electricity. Yeah.
Let me challenge you there, though. You're saying it's not the rating of the motor. Where, if it wasn't the rating of the motor, where would the extra energy go? Let's say let's keep the numbers easy. Let's say we have a 100-watt fan. And if you're telling me that 100-watt fan puts anything but 100 watts of heat in the room, where does the other heat go? Where does the other energy go? And how come if I leave the fan in there for several days, something doesn't get really hot?
Okay, a good example. If you would look at the 100-watt ceiling fan, I would say if you're gonna use a 90% efficient motor, which most brushless DC motors are right now, or AC motors, excuse me. So you would probably assume 10% of energy loss. 10% that's going through that's heat radiating from the motor casing to the room.
Okay, so far we've got 100 watts going in, 10% goes straight from the motor as waste heat into the room. Okay, what happens to the other 90 watts of energy, of power?
It goes into moving the rotor of the motor, moving the blades into the room.
Okay, and then what? Then where does that heat end up where does that energy end up dissipating? Kind of.
That blades of the fan moves the air molecules into the room. So you would get a couple things initially when you turn on the fan. If you have stagnant air into the room, because air is fluid. Even when you study it in engineering school, they call it fluid dynamics, and it kind of covers air and gas, because you could go from either. You could go from gas.
Okay, so no, I
to
get it.
air.
you're raising an interesting point there. You're saying before you put the fan in, the air was fairly stationary, and after the fan, after a period, the air is circulating in the room. So now the room has some kinetic energy, some movement energy in the air, right? But eventually,
Right.
the fan is going to bring that room's that circulation is going to settle down eventually, and you'll have put all the energy you're going to put into the movement energy in the air. And it's just a constant circulation. So then, in the steady state, in the long run, then where does the extra energy, that other 90 watts that didn't come straight out the motor as heat, where does that end up?
It ends up moving the molecules of the air back and forth into the room. So that
Yeah, but
energy would eventually heat up the air into the room
yeah,
because
exactly.
these air molecules are going to be, you know, colliding with one another.
Yeah,
If
yeah,
it's a closed system and you keep a
yeah,
fan on with a 10%, you know, using that example that you put out, that room
yeah. So you,
temperature, that room is going to go, that temperature is going to go up uh, in a steady state,
yeah.
I
So
would
can you
assume.
see that my claim in the long term is I like to point you put about the room will end up with more kinetic energy in the air, movement energy, because it's now moving and it wasn't before. But once that's all settled down and the room's in its new state, I would still say that every single watt of heat, electrical energy you put into that fan turns into heat. 10% of it, in your case, directly out the motor, and then the other 90 watts via the air, moving around, bumping into things and dissipating as heat. You're still, all of that must end up as heat, because if it didn't, it's going to, either the kinetic energy of the air in the room would have to keep going up, in which case you'd end up with a hurricane in the room. We know that doesn't happen. And if we don't end up with a hurricane in the room, then we must end up just with a constant 100-watt heating effect in the steady state once it's all settled down. Do you agree with that?
Yeah, I agree with that. I agree with your last assessment there, because definitely the blades moving the air is definitely going to heat up the room. So I could definitely see it,
Yeah, but you
consider it
brought
as
some
a
real nuance and interesting stuff there, which I hadn't considered, which is this intermediate bit about making the air dynamic and moving and having kinetic energy that could do real work. If the room was gusty enough or windy enough because of the presence of this fan, think of an air tunnel, a wind tunnel, then obviously the kinetic energy of the air is a huge part of it. If I say to you, well, let's not go into that in any more detail. So anyway, thanks for bringing that bit. I think that's important. But long term, in the steady state, the fan heats up your room to exactly the amount of the plate, the electrical plate on it. If it's 100 watts, it's 100 watts of heat in the long run. So back to you, Hero. John, John, then Hero.
I may be in the matrix. Do you hear me?
I can hear you, just about. Yep, we got you.
Okay. Well, I was just going to say, and maybe Andy was going here too. I think the rating of the motor is not necessarily the amount of energy that the motor is using. It depends on the speed of the fan, depends on whether it's accelerating up to speed, et cetera.
Yeah,
Right?
sure. Yeah. I mean, the actual measured electrical energy, let's put it that way. Yeah, not necessarily. I mean, I say just looking at it, that's a bit trite. Obviously, that your motor is probably not, as you say, using its full power. So you'd actually just use a kilowatt or a similar device in the wall and measure the voltage, multiply by the current, and whatever you get there, that's the amount of electrical energy going in. That must be ultimately the amount of heat energy ending up in the room. Otherwise, something is starting to move real fast somewhere, which is obviously not what's happening. So then, Hero, you said not all of the energy of the fan. The reason that was a big side, because tangent, you said not all of it's becoming heat, but actually I would say all of it is becoming heat.
Well, I don't think I said not all of it's become heat. My point is, if it was a 100-watt motor, for example, that's just not a lot of energy. So no one would buy a 100-watt heater, right? Heaters are 1,000 watts, 3,000 watts. So it would just be a sucky heater. It wouldn't be very
Oh, I
effective.
see.
It wouldn't
That's a
room up
very
much. Yeah.
Yeah, that's a very valid point. Yeah, I mean, that's one of the reasons we get away with the fan, right? And segues us beautifully into the third part of the question, is that we can live with 20, 50, 100 watts of extra heat coming out of our fan because, and why? So then the last part of the question is, why do we do it at all then? It's putting heat in the room. It's costing us electricity. We're trying to be cool. Why do we do it? It's kind of
Well,
obvious in a way, but people don't necessarily think about it. Yeah, Hero, go ahead.
but in between there's another reason why it would actually make the room feel warmer, which is that it's going to transport warmer air that's up high down low. That might not be a net increase, but it's going to take what feels warm and put it in our faces. So to me, that I thought that's what you're going to say, like it's transporting air around.
That's valid, yeah.
Yeah.
Yeah, and despite that, we still use them. So despite the fact it's taking the hot air that's risen to the top of the room and pushing it back down on us, which is another good point, we still use fans. And they still do make us feel cooler. So it's very, why? And the answer was earlier on, by the way. We talked about wet bulb and dry bulb temperature. The
Yeah.
answers are,
Evaporative cooling.
yeah, exactly. It's just the way that our skin works. It actually doesn't help a dog, for example, very much at all. A lot of animals can't sweat. I don't know how many animals can sweat. I don't want to make that claim. But I know that dogs aren't very good at sweating, and they lose most of their heat through panting. So you put a fan on in a room with a dog, it might help it pant its heat away better. But apart from that, it doesn't care because it's not sweating anyway. It's about the fact that at our skin, we evaporate moisture to lose heat. And if you don't have a fan and the air is still, then you very quickly end up saturating. You do two things to the air around your skin. Firstly, you make the air around your skin warm and it sticks to you in the boundary layer near your skin and stays warm, which makes it harder for your body to lose heat. And secondly, it ends up moist. So it ends up warm and moist right next to your body. And what the fan does is it constantly, which is why we like a cool breeze as well outside, it constantly removes that warmer, moist air and lets our body continue to sweat effectively. So effectively lowers the wet bulb temperature in the room, even though it will increase the dry bulb temperature very slightly. So that thermometer that you put in the room in the shade, it will be in the shade if it's in the room, will actually show after a long period of time a tiny increase in temperature due to the fan, everything else being equal. Not very much, as Hiro says, it's not a very good heater, it's only 100 watts or whatever. But the wet bulb temperature would, if that wet bulb was in the airflow, will show a more comfortable lower temperature because of its evaporation is being helped by the fan. So there's a subtlety, and that's why I introduced wet and dry bulb really early on. I think that's everything I wanted to cover. I know that family have just arrived home, probably armed with dinner, so I might need to run in a minute. But yeah, just any final questions or comments? I just wanted to. Otherwise, I just want to thank everyone for being here and say come back next week for John. John, you're going to be back and running it next week.
What
Yes,
happens in Vegas stays in Vegas.
exactly. Yeah, no, I should be back next week. I just thought maybe I'd just throw out one thing. I don't know if you want to talk about this at all. Maybe we can just leave it as a final question. It's also kind of an interesting thing that when you're in a room, you're just sitting in a room, feeling the way you feel, and everything in the room has come to room temperature, and you reach out and touch, an iron railing or anything metal. It feels cold. Right? I mean, you're in the room, it's the same temperature as the room, but metal always feels cold.
Yeah, that was the question that I deleted and then didn't
Oh,
address
okay.
just because of
Sorry, I
time.
came in late.
No, well, we covered similar things like when we talked about touching aluminium foil and we talked about the hot coals. We already kind of talked about the importance of the thermal conductivity of the thing you're touching. But yeah, maybe we'll leave that as an open question for people to think about rather than spoon feeding all the answers. But we've already given you enough to answer that, I think, given the other material. I think that's probably it for now. I'm going to go just in case my wife has arrived home with a fistful of food that I need to go and eat. Plus, I'm a bit unwell, so I want to just get better. So thank you, everybody. It's been a good turnout, actually. Thank you for being
Thanks,
here.
Ben, for doing this.
Yeah, no worries. It was a rehash of a previous Bite to Physics, but I had enough energy to do that, not quite enough to make a whole one from scratch. Thank you, everybody. If you like sciencey things and a bit of fun, I am, I've had nearly a month off YouTube, but I am back to it as soon as I'm better, which will probably be in a week, about a week. There's a link at the top of the room and a link in the chat to smartview.tv, mainly covering electrics, but there's also some science, especially in the shorts, there's a lot of science curiosities and experiments and fun stuff like that, kind of Vsauce, Veritasium type style stuff. So welcome to join
But
me over there.
let me also put in a plug for Shamash, who's not, because he may feel reticent to do it. But his philosophy Wednesdays are, I think, really fun too, because he's a sciencey kind of a philosopher, and I find them particularly interesting. He had a really good one, I think, this Wednesday. I haven't told you that before, Shamash, but that was a really, really nice, especially the first 8 slides, as you know. But Philosophy
Thank you.
Wednesdays,
Thank you.
same time on Wednesdays as it is on Friday.
8 slides is some magic number. All of my bites of physics that I've done for you have had 8 slides for some reason, John. So maybe that's the way. Maybe you do just 8 slides and then they're good, and then from the 9th one on it will
Yeah,
go.
maybe. I think that's something. I mean, mine usually work too.
Well, yours have been great recently. The amount of effort you've been putting in, it's really good. So, all right, people, thanks very much for being here. Nice to see you all. I'll be casually on and off Clubhouse over the next few days, my normal kind of dishwasher times and that. But otherwise, see you the next time John can't be bothered to do your bite of physics. No, I'm only kidding. Next time he's illicitly going to LA to, to where are you going? Vegas, to go and do whatever you do in Vegas. And enjoy yourself, John. Do check out Shamash's rooms, as John says. This is rewatchable on YouTube. Shamash, can you paste the link to this rewatchable?
Will do. I've been
session
pasting
into
it
the
during
chat?
your talk, but I will do, of course, at the end.
That'd be awesome.
Just go to YouTube and type Scientific Discourse. You will find a link to Ben's channel. You will find a link to John's channel, and you will find playlists of every lesson we've done for the past, let's say, 4 or 5 months. So there you go.
Awesome. All right, guys, I think I'm just going to end the room sharp rather than playing music out so that I can get up and move around. And yeah, nice to see you all and see you next time. Thanks for all your contributions, everybody.